So I'd like to tell you today about some exciting new results that we've gotten from the studies of samples brought back to Earth from space by the Stardust spacecraft. Stardust was a NASA mission that was really two missions in one spacecraft. I'll talk about in a bit. But this was the very first spacecraft ever to bring back extraterrestrial samples from beyond the moon. And so we're incredibly lucky to have these samples in our labs. So we're really interested in trying to understand the first couple of million years of the solar system's history. We're trying to understand the process by which materials in the interstellar medium came together to form the solar system, the sun, the planets, the comets, the asteroids. And we're particularly trying to understand the original building blocks of the solar system. And the problem we have is that these building blocks are almost entirely absent from most of the materials that we have access to. And so not only do the studies of these materials tell us about our own solar system, but they also tell us about solar systems that are forming right now. This is a picture of an object called HH30. It's a solar system being born right before our eyes that we can see in telescopes. So this original material in the interstellar space is, by astronomers, called dust. And I really don't like the term. I mean, who wants dust? But they're actually rocks in the classic geological sense of assemblages of minerals. This is what this dust looks like when we look at the plane of our galaxy. So, as I mentioned, the Stardust spacecraft was really two missions in one spacecraft. The first part of the mission was to collect samples of material from a comet, from a Jupiter family comet called VIL2. And it flew past this comet at about 6.1 kilometers per second, many times the speed of a bullet, and captured particles from the comet in a weird material called aerogel. I'll come back to that. The other part of the Stardust mission was to collect the very first samples of actual materials from outside our solar system, the stream of interstellar dust that's coming into our solar system, which is the result of the motion of our solar system with respect to the local interstellar medium. It's a little bit like driving down a highway in a snowstorm. When you do that, you see snowflakes coming at you from one direction, and it's the same effect. So the Stardust spacecraft came, or the samples came back a few years ago in the Dugway Proving Grounds, and I was very lucky to see this along with my family when it came in. It came in at record high reentry speed and has been incredibly fun to work with. So this is one of the first particles that we extracted from one of the aerogel tiles that was used to capture these particles. Aerogel is a bizarre material. It's only a few times as dense as air. If you hold it in your hand, it's like holding a ghost. You can't really feel its weight. But it has the property that it can capture particles going at many miles per second, practically intact. So this is what, you can't even see the particle here. It's a track from the comet, and here's what it looks like under a microscope. So this is a cometary particle that got captured in the aerogel and extracted in this doorstop-shaped wedge of aerogel. There's no doubt that these are the most challenging extraterrestrial samples ever returned. They're tiny and they're incredibly hard to work with, but that is what makes it really fun. So an example of some of the science we've done with the cometary collection from Stardust is this. This is a study that we did at the Advanced Light Source of a particle called Iris. This is the X-ray map of Iris. It's a particle that's only 16 microns in diameter. So a micron is a millionth of a meter. This is an incredibly tiny particle. But in fact, it's a rock full of individual minerals. And it turns out that this particle told us about the timing of the largest object in the solar system other than the sun, the planet Jupiter. So this was an example of the kind of exciting science we can do with these new materials. The other part of Stardust was the interstellar side, and that turns out to be vastly more challenging than the cometary side. If we got a tiny little bit of material from the comet, only about 300 micrograms of material, we got less than a millionth of that, we think, from the interstellar dust stream. So this is a really small collection of materials. And our first order challenge, in fact, was to even find the particles in the collector. And so we took a very unusual approach in doing this, and we constructed a project called Stardust at Home, in which amateurs, that is citizen scientists, are helping us to identify the impacts in the aerogel through searching through digital images that were acquired by an automated microscope. And so at this point, more than 32,000 people have participated in this project. They've collectively done more than 100 million searches. It's a mind-boggling amount of work. And at the close of our first phase of our project, we had discovered 72 tracks. And when I say we, it's really not the people in our lab, but the citizen scientists who've been doing the searching. And now we're up to more than 130 tracks that have been identified, not by us, but by citizen scientists. So this is the first of the interstellar candidates that we have identified in the Aerogel. This is a particle called Orion, and this was analyzed using an X-ray microscope, or two X-ray microscopes the size of shopping malls. One of them is it's the Advanced Light Source at Lawrence Berkeley Lab, and this is an X-ray map of this particle in three different elements. We can do spectroscopy. This tells us about the minerals that are present. And we can also do X-ray diffraction. This was done at the European Synchrotron Radiation Facility in Grenoble, France. So this is a particle that we think probably formed around another star and then had a very complicated history in the interstellar medium before it was captured by the Stardust spacecraft. By the way, it was discovered by an amateur named Bruce Hudson. He's a retired carpenter in Ontario, Canada. So this is another particle. This is an enormous particle. This is the track that it made in this piece of aerogel. And this is track 40, for whatever that's worth. And this particle came in at such high speed, about 20 kilometers a second, that it turns out that very little of it survived. We think it just left this track. But that by itself tells us some very important things about interstellar dust. We also found 4 candidates in the aluminum foils that were on the spacecraft between the aerogel tiles. And these are some X-ray maps that were taken of these 4 particles. And the amazing thing about these is that they're all different. So I think that the central excitement, really, for us about this is that we've taken the first baby step in observing interstellar dust, not through telescopes, as astronomers have been doing for decades, but instead through microscopes like the Advanced Light Source. And so our progress in viewing interstellar dust has gone from the scale of light years to the scale of nanometers. It's about 27 order of magnitude improvement in resolution. So that doesn't happen every day. Thank you.